find an interval of convergence for a power series like this, we think back to what we did with regular series. And our most, in my opinion, our most powerful tools for regular series were the divergence theorem, the interval convergence test, and the ratio test. And that's what we're going to use most of the time. So what does the ratio test tell us? Ratio test says, look at the ratio of consecutive terms, an plus 1 over an, check out their absolute value, find the limit as n goes to infinity. If that limit is less than 1, then we have convergence. If that limit is greater than 1, we have divergence. And if the limit equals 1, it's inconclusive and we got to use another test. When will it equal 1? At the endpoints of the interval that we end up with. So then we have to find some other thing to test them out. Let's apply that here and see what happens. So first, let's just figure out what the n plus 1 versions are. So that's going to be x minus 2 to the power n plus 1 divided by n plus 1 times 3 to the n plus 1. That's my a sub n plus 1. To divide by an, I could just multiply by the reciprocal. So I'm going to do that. The reciprocal of an would be n times 3 to the n over n x minus 2, excuse me, the power n. We've cleaned up things like this before, right? Technically, this has absolute value around it. Let's throw those in. We'll worry about the limit in a minute. Now, a bunch of stuff cancels here. The factor of x minus 2, there's one more on the top than the bottom. So basically, all n of those cancel with n of those, leaving one of these in the top. So I'm left with an x minus 2 from that cancellation. Similarly, 3 to the n in the numerator versus 3 to the n plus 1 in the denominator, there's one more 3 in the bottom than the top. So I'm going to have it divide by 3 there. And then I'm stuck with the n over n plus 1. That doesn't really cancel in any significant way. And I still have the absolute value of that. So this doesn't clean up much more than that. But now I'm ready to take the limit. What limit am I taking? I am taking the limit as n goes to infinity of all of that. And the only place I have n's is right here. And we've seen limits like that plenty of times. That's basically a rational function of n. The degree of the top is the same as the degree of the bottom. And so this is going to converge to the quotient of the leading coefficients, which is 1 over 1. So this limit equals absolute value of x minus 2 over 3. And this will happen a lot with these series. Okay, next, what does the ratio test say about the limit? It says that limit has to be less than 1. Okay, check it out. This 3 in the bottom is positive. I can pull it out of the absolute value and multiply it to the other side. So I could also write this result as the absolute value of x minus 2 has to be less than 3. Well, that right there is an interval of convergence. This says on a number line, 2 is the center, and you can go at most 3 to the right. Oops, my hand got ahead of my brain. 2 is the center, we can go 3 to the right. 2 plus 3 is going to give me 5 on this side, and 2 minus 3 to the other side is going to give me a negative 1. So what do I know at this point? Well, I'm not sure about at negative 1 or at 5. Those are question marks. But I know that in between, any number I pick in between here, I'm going to have a convergence series up there. Okay, before I do the endpoints, let's just check that. Let's just pick some number in between negative 1 and 5, like 4, for example, is in that interval. What happens if we plug in 4 to my original? Well, I will get 4 minus 2, which is 2. So this will equal, let's get a new page here. So if x equals 4, then I'm going to get the sum as n goes from 1 to infinity of 2 to the power n over n times 3 to the power n. I'm going to rewrite that just a little bit. That's the sum as n equals 1 to infinity of 1 over n times 2/3 to the n. Well, that is partially a geometric series. R is 2/3. So this is like a geometric series. It's not quite a geometric series. What test of series would help me confirm that this is convergent? Not the ratio test, because the ratio test, will ratio test work here? Oh, it actually might. Or we could do a limit comparison test. I want to go for the limit comparison test since we just did a ratio test. Limit comparison test, I'm going to compare this to the sum of 2/3 to the n. Limit comparison test says look at the ratio of the two sequences. So what's the limit as n increases of the sequence you're wondering about and the sequence you know about? So I'm suspecting this converges like the geometric series 2/3 to the n. Well, that cleans up nicely. The 2/3 to the n divide out. This becomes the limit as n goes to infinity of 1 over n, which I know goes to 0. And the limit comparison test says if the limit is 0, both series must converge. If the limit was any real number otherwise, then both series do the same thing. Either both converge or both diverge. So by the limit comparison test, then the series I'm interested in definitely converges. So I just picked one of the numbers to test, but the bottom line is, according to the ratio test, it converges for every single number in this interval. What I don't know about is the endpoints. So let's check the endpoints. What about x equals -1 and x equals 5? Let's see. So this was just a fun check. It wasn't necessary. But just in case we didn't believe the ratio test, now we have to check the endpoints for sure. So endpoints, one of the endpoints was x equals -1. So that means I would have the sum as n goes from 1 to infinity of -1. What was it again? -2 to the n, bless you, over n times 3 to the n. Well, -1 times -2 is -1 minus -2 minus, sorry, -1 minus 2, there we go, is -3. So I have the sum of -3 to the n over n times 3 to the n. I can clean this part up. That's really -3 over 3 to the n, which is really -1 to the n. So then this becomes the sum of -1 to the n over n. What do we know about that series right there? That is the alternating harmonic series. And we used the alternating series test on this before to show it converges. So this right here is the alternating harmonic series. In our work in previous weeks is that this converges according to the alternating series test. So back here, I can go and shade in this circle right here. I have convergence at that endpoint right there. What about at 5? Page, what is the sum as n goes from 1 to infinity of 5 minus 2 to the n over n times 3 to the n? That's going to be the sum of 3 to the n over n times 3 to the n. And the 3 to the n's divide out, and I get the sum of 1 over n. What do we know about this one? This is the harmonic series. And way back, one of the first things we did when we were playing with series is we showed, based on the integral test, that this diverges. Now, I happen to end up with two series that I was familiar with from my previous work. If it's a series I'm not familiar with, then I have to actually do the test to show it. So otherwise, if you weren't sure about that, then the integral test says check the integral from 1 to infinity of 1 over x dx. And see what that does. So I'm going to skip that right there. So what do I know about the series I just started with? So I have the power series n equals 1 to infinity of x minus 2 to the n over n times 3 to the n. And the ratio test gave me a radius of convergence of 3. This series was centered at 2. So again, looking at the number line, put 2 in the middle, add 3 to get 5. Radius can also go the other way, so we can subtract 3 and get -1. And we just discovered by using the integral test on this side that that's an open circle. We do not converge there. At -1, that was the alternating harmonic series that does converge. That's a closed circle, and then every number in between. So this series here converges if x is less than 5 or greater than or equal to -1. What does it converge to? I have no idea. But it's a function. What happens if we graph it? Well, we can't graph all of it because we can't do an infinite sum on a finite thing like a computer, but I can do some partial sums. So the sum from 1, let's go up to 10 of the fraction x minus 2 raised to the power n divided by n times 3 raised to the n. Let's turn off this other one. It looks like this green thing right here. Now, as far as this green thing goes, let's change the zoom on this a little bit. Let's see. I have a radius, an interval centered at 2 that goes out to 5 on one side and -1 on the other. I only added 10 terms. I wonder if Desmos can handle 100 terms. Maybe. So in this case, it looks like it can handle, pretty well. Now, again, my series should be converging out to 5. And this thing is starting to take off around 3. That could be a natural version of this function, but it could be we just haven't added enough terms to see what's happening at the endpoints 5 and -1. And I think if we try to type in 1,000, we're really going to slow this thing down. I got a little pointier over here on the corner. Interesting. So it's possible this is a function we didn't know about until now. That's not any known function other than expressing it as a series like this.